So with this lesson, we're going to be talking about systems of linear equations, and specifically we're going to look at solving them. The method we're going to be looking at for solving is the graphing method. So the standard that we're focusing on talks about that what we need to accomplish is be able to analyze and solve pairs of simultaneous linear equations in the 8th grade. We want to be able to understand that the solutions to them is going to be a point of intersection of their graphs, because the points of intersection satisfy both equations simultaneously. Okay, so what we really we're looking really at that standard, what we need to break it down to is we need to make sure we understand what is a system of linear equations, and then how do we actually determine that solution to the system of linear equations using this method that's called the graphing method. And then we want to make sure that we understand that there's different types of solutions that we may find when we're solving a system of linear equations, and what those are and how we'll recognize them. Okay, so what is a system of linear equations? So a system of linear equations is when you consider two or more linear equations. So in other words, remember their graph is a straight line. We usually go ahead and use the variables x and y. They're both to the first power. They are usually going to, remember, they are added to each other or subtracted from each other, never multiplied or divided. So those are the things that go into being a linear equation. And so typically what we're looking for is, when we're solving it, is that solution or the point where the lines intersect. Because remember, the points on each line are its solution to the one line. But since we're looking at two lines, we want to look at that. That's called our system, okay, because we have more than one line. And so in order to have a solution to a system, that solution to one line has to be a solution to the other line. In other words, it has to be a point that is a solution to both equations, or we have to actually see that the point belongs to both lines when we're using the graphing method that we're going to be doing. So there's two methods for solving a system of linear equations that we are going to be using in 8th grade. One is we're going to be using the graphing method, which we're going to be working on in this lesson, where we graph each linear equation on the same coordinate plane, and then we determine the point of intersection, which we know is our solution. Okay, so the solution is going to be the ordered pair x, y. The second method that we're going to be looking at later on is an algebraic method. So we're going to look at solving a system of linear equations algebraically to determine the coordinates algebraically, what is x, and then what is y. Okay, so how do we go ahead and solve a system of linear equations by using the graphing method? Okay, so our steps are, first, we graph each line on the same coordinate plane. We determine the point of intersection. There's a little asterisk here for a reason, because sometimes there's an issue with what is the point of intersection. Okay, and then we verify our solution. So by substitution, which means you algebraically replace the x and y into each equation separately that you got for that point of intersection, okay, with the numbers for the coordinates of it. And you make sure that it does satisfy both equations. Okay, so let's go ahead and try it. So here we have two linear equations. Y equals 1/2 x times x minus 2, and y equals 3 times x plus 3. So according to our steps, we graph each line on the same coordinate plane. So let's go ahead and do that first. So I'm going to call this first one line 1. So that's our line 1. And the second one here is going to be my line 2, just so we can kind of keep them color coordinated. Okay, so what is my slope for line 1? So let's go down here and put our information for each line. Okay, so our slope for line 1, so I'm going to put slope 1, remember, is the coefficient of x when it's in slope-intercept form. So my slope is 1/2. I also know it's y-intercept because it's what we're adding or subtracting from the x term when it's in slope-intercept form, which means my y-intercept is -2. So when I'm graphing in slope-intercept form, I first go ahead and I graph the y-intercept, and then I use rise and run. In this case, because the slope is positive, my rise is going to be positive and my run is positive, or they could be both negative. So if my rise is +1 and positive 2 is my run, then I would go up 1 and right 2. If they're both negative, then I would go down 1 and left 2. So just make sure you can remember you have enough points so that you can, let me fix this one because it's not exactly on the y-axis, so that you have enough points to have a good understanding of where the pattern is for your linear equation. Okay, so then you're going to go ahead and graph your line, and you want it to be, stretch it out, make sure that you are having it long enough because you're not sure yet where they're going to intersect. You're just kind of hypothesizing, that it's going to be somewhere, and you're hoping it's going to be in that area, not off the graph. Okay, so now let's go to line 2. Okay, so for line 2, what is our slope? So again, we go to the coefficient of x. So my slope for the second line is +3. Remember, it has a hidden denominator of 1, and since it's positive, again, the rise and the run are either both positive or both negative. Okay, and then my y-intercept is what I'm adding or subtracting from the x term. In this case, it's +3. So I'm going to go ahead again and graph my y-intercept. And then I'm going to go ahead and use rise and run. So this time I'm going to go up 3, 1, 2, 3 over 1. And next I'm going to go ahead and go down 3, 1, 2, 3 over 1. Okay, on the second line, sometimes I like to do more just so I can see if I end up finding out what my y-intercept is. So this time when I go ahead and I see that they're getting close to intersecting, so if I go 1, 2, 3, so I'm using negatives for my slope, -3 and then -1 for my run, I end up with a point that's right there on the line. That means that point is the point that lies on both line 1 and line 2. So I'm going to go ahead and I'm going to finish graphing. Okay, so what is my solution? So to go ahead and say the solution, you need the coordinates. So you need an x value and you need a y value. So we go to this point where they're intersecting. And what we're saying is that out of all the infinite points that lie on line 2 and the infinite points that lie on line 1, this point right here is the only point that lies on both lines, so it's the point that solves our system. Okay, so what are its coordinates? Okay, well, its x coordinate is to the left 2, so that's -2, and then it's down 3, so it's at -3. So now let's see if it actually solves our equation. So our equation for line 1 is 1/2 times x minus 2. So if this is a solution, if I replace the x with -2, because remember, this is my x and this is my y, I should get -3. So half of -2 is -1. Remember, -1 take away 2 means add the opposite. -1 plus -2 is -3. So it does work for line 1. Now, if you made a mistake in your graphing, then it wouldn't satisfy both of the equations. So that's why you do have to go ahead and verify the second one as well. Okay, so let's go ahead and verify for line 2. Okay, so line 2 says y equals 3 times x plus 3. So we're going to go ahead and, again, replacing the x with -2. We want to make sure that we end up with -3. So 3 times -2 is -6. And -6 plus 3 is -3, which means we have verified that this point right here with coordinates -2 for x and -3 for y is our solution. Okay, so again, what did we do? Okay, we graphed each line individually. Okay, we analyzed the equations first to figure out how to graph them. You also can make a table of values for each one. Then we went ahead and we've used our eyeballs, okay, our eyesight, and we looked for where the lines intersected. We found out the coordinates of it, and we said that's our solution. To make sure that it was our solution, we substituted into our equation to make sure that when we replace the x coordinate with the given value that we were our proposed solution for x, we ended up with our proposed solution for y, and not just in one equation, but in both equations. Now, just like with an equation with one variable, you could end up with a system of equations with different types of solutions. So when the lines intersect, like our first system that we did, okay, where you see the lines crossing somewhere, or they would eventually cross, that's going to tell you that you have one unique solution. What's true about the slopes is the slopes are always going to be different. They could both be positive, they could both be negative. Like in our the system that we did, they were both positive. But the slopes cannot be equal. So the slope of line 1 is not equal to the slope of line 2. Okay, and that, if you see that the slopes of the two lines are the same, you know that you're not going to get one solution to your system. If the line's slopes are different, then you are going to get one solution. Okay, let's look at the second one. Okay, these lines are heading in the same direction. The distance between them is exactly the same when you look at them perpendicularly, so or at a 90-degree angle, which means they're never going to intersect. Okay, and that's because they're parallel to each other. What that means is that the slopes of the two lines are equal to each other. Okay, but what's different about them is their y-intercepts are different. So the y-intercept of the first line is not equal to the y-intercept of the second line, but they have the same slope. And that's going to be no solution. They never intersect. They'll never have a point in common. Therefore, there's no solution. Okay, the third case we have is we go ahead and we graph our first line, and then we graph our second line, and we notice that it's just the same line again when we graph the second one. So what do they have in common? Well, that means, for example, like I'm using green and blue, that every point that's on this green line shares in common every point with the blue line. Now, just because I don't have them drawn exactly the same, remember, arrows indicate going on to infinity. So if we stretched this blue line out into infinity in this direction, or if I stretched it in this direction and as well as the green line, they still would have all those points in common. Okay, so what that means about the equation of the line is that the slopes are exactly the same and the y-intercepts are exactly the same. And that's because the equations are exactly the same equation. It's just maybe when you go ahead and you actually are given the equations, you probably was given to you so that one had a formatting that was different than the other. So you just maybe have not recognized it until you graphed it. So What we call this is they are coinciding lines. The lines coincide, or they share all the same points. So coinciding lines, or the lines being exactly the same when you graph them, have infinite solutions.